CNTL3020 2026 winter controls 2 ELN2 second term. Fanshawe College, London, Ontario. Week 10. All right. I need some kind of a bells and whistle to have like a radio signal. Never mind. All right. So, I was approached by someone today during the in-person class with the request to expand a little bit on all the other Boolean algebra laws because we just did the De Morgan's theorem, and I wanted to drill that because that would help us, and it did, with the labs that we are doing currently with the PLCs. But there are all the other ones, other laws of the Boolean algebra, other laws or properties, as they're being called in different ways by different sources. And I felt, anyways, that they were a little bit neglected, and I was reminded by one of the students that maybe we should so here's an opportunity we can use to expand on some of the other laws. So we're going to go through some of that, and some of the, well, actually most part of the test that is going to be, it's going to be on this stuff here that we're going to do. However, during the test, you will have the formula sheet as you had last time, because I'm not expecting you to remember all the formulas. When you go to work, you're not going to be expected to memorize all the formulas. You're going to be expected to know where to look for them and how to apply them. So that's how we're going to do it on the test as well, to be fair. Plus, I understand that you have all the other subjects to deal with, and you have another 2,000 formulas to apply. So let's just make something that makes sense instead of me drilling you with, torturing you with trying to remember the formulas. And if you don't get it right, I'll get you. No. Let's be nice here. All right. So all the other formulas that we kind of touched upon before, but we didn't spend enough time. Are these here? Here we have the distributive laws, 2 of those, and I put them at the front here. When we have 3 inputs, 3 variables, A, B, and C, if we see something like this, and of course the Microsoft Word is being silly with me here. It's the same as this. All right. Here, stay there. Or if you see something like this, which would be A or B and C, it's same as A or B and A or C, and these are in parentheses here. So these parentheses are important in this case. Over here, over here, you can drop the parentheses because the order of operation, if you drop the parentheses, the order of operation is going to be we do the AND operators first and then we OR it. But just so things are visually more comfortable for us humans, we kept them on for those, the parentheses, we kept them for us to better see that while we're learning. But if you see that without parentheses, well, maybe if you do things enough, you're going to see it. So that's the whole thing. With these, I can talk until I'm blue in my face. And it's going to give you some information, but unless you go through it and do the exercises enough, then you won't get it. Right? So I would encourage you to practice this type of stuff. And with the technology that is right now available at our fingertips, you can easily do that. Yes, thank you, Mitchell. That April 3rd is the Good Friday, so next week. But with other classes, you probably have some classes that were going to be canceled, of course. But with our course, this 3020, it's the controls too. We don't have any classes, so we are safe. All right. I was just looking at the chat line here. All right. So here's the distributive law. Let's just clean this up a little bit. What do we have here? All right. And then there's another absorption law. A or, and here is the A and B, which we can drop the parentheses here, but for the visual effects, it looks better for us and easier for us to see. You see thing here? All this one here, it's same as A. What does that mean? That means that this is being absorbed by the A input. Whatever A is, the output is going to be. And we're going to prove that. And over here, same as the other operators, if you see that, now in this case here, you have to keep the parentheses because, so you do the parentheses first operation and then end it with whatever else is here. If you see that expression, then also the output is following the A only. Doesn't matter what B is. Basically what this one says, whatever the B is, who cares? The output is going to be whatever the input A is. So I'm going to show you a couple of different perspectives of how you can look at that and how you can solve that to make your life easier for you. All right, so I multi-simmed that particular scenario here. And you can do the same thing with all the other ones. So I'm going to pull up my multi-sim situation here. And over here on the right side, I just placed all the gates there so I could just grab them as I need them. And over here we have the circuit. How is that? Because that's the same one. See the absorption? I just copied that here and pasted. So here's A or A and B, same as A, or A and A or B, same as A. And these will be the logic gates that I put on the multisim here. So what do we have here? That OR operator is this gate right here. This AND operator is this gate right here. That's the AND gate, that's the OR gate. And then we do the connections here. Here's input A, input B. All right, same as we all have two variables. And according to this statement, if we connect the circuit as such, which is connected like that here, because look here, we have the A going, and it's applied to that OR gate here. So one of the inputs is A. But also, we have to apply the A to one of the AND gate input. So that goes into that input and that goes into that input. If you look at it, it's going to make sense. And here is the B. It's only applied to the AND gate, which is here. And over here is something that's called a probe in multisim. If it lights up, that means it's a logic 1. If it doesn't light up, it means it's a logic 0. On the bottom, we have this equation connected in gate. So you can do the multisim if you want. Multisim is actually really wonderful for this type of application. As long as you don't get like 1,000 gates, then it's going to start choking up on you. But you can also, for fun, you can use the 74 series of the chips, 74 family. So it's 74 something something. I forgot what it was. It's the OR gate. 74 something something else, like 2 other digits. It's going to be the AND gate, connect that on the breadboard, and you get the reality of things. You have to connect it a certain way. I think you're going to have like the experience in other classes here, but you haven't had that so far from what I'm getting from you. So if this is true, then this should behave as this says so. Let's put it to the test. I'm going to press the play button to start the simulation. So the simulation is on. If we change this logic input of A to 1, the output should follow. So far it follows because A is 0 and the output is 0. And according to this, it doesn't matter what B is, it's still going to be what A is. The output still will be what A is. So let's just play with the B input, see if it makes any difference. It shouldn't. Okay, I'm changing it from 0 to 1. The output does not react. So far, so good. Now let's change the A into logic 1 from 0. Then this should follow. Whoa, all right. Change it back to 0. It follows. Now, if B is 1, it shouldn't matter. This still should follow. The output still should follow this A input. And it does. Whoa, the magic, right? All right. In this case here, we should have the same thing. Let's try it. Okay, B, we change it from 0 to 1. Nothing happens. As soon as we start changing A, the output is going to follow A input. Oh, wow. Same thing. Change that, doesn't matter. Change that, it follows. So here's one way of looking at this. And there's also another way that I'm going to show you. Let me just bring up the screen here. I made a little table. So we're looking at this. Let's say, what can we do? Or the first one or the second one to prove it on the table, on the truth table. Let's do the second time. I think I did the first one last time. I'm not sure. I don't remember. Well, I might have done it twice. Let's do the second one. So we're looking at A and A or B. So we're looking at A and A or B, and that should give us A. All right? A and A or B. A and A or B equals A. Good. Let's put that to the test with the truth table. All right, so we have input A. Actually, you know what? Let's do it. Let's get into a habit of doing the least significant bit and the more significant bit on the right side. So least significant bit would be on the right-hand side, and the most significant bit, or the more significant bit, it was going to be, so there will be C, D, and so on the left side here, just like we are writing the numbers. All right, so here's the input A, here's the input B. What possible combinations can we have with those? We could have both of them logic 0. We could have one of them logic 1. We could have the other one logic 1, and we could have both of them 1. These are the only possible combinations because we got 2 bits, and we are binary, and we're looking for just it, so we have 2 bits, binary 2 bits, so 2 to the tooth. 2 to the second power of 2. That's going to equals 2 times 2, and that equals 4. So a 1, a 2, a 3, and 4. Okay, combinations. If we have 3 bits, would be 2 to the 3, and that's going to give us 16 combinations. No, 7 combinations. All right, so let's take care of this part first. So A or B, that's going to be the logic here. A or B. What's the OR function that's going to be here? So the result is A or B, 0 or 0, that is 0. According to the OR logic, 0 or 1, that's going to give us 1. 1 or 0, that's also going to give us 1. And 1 or 1, it's also going to give us 1. So that's the OR logic. We just took care of this part right here. Now, we have to end this part here with this part here, and that end is going to be here. So, all right, so we're looking at this part only here, and we're going to end that with what? With the A, because this one we took care of, so we're going to end that with A. So this is going to look a little bit different. Yeah. So that here, this and that is going to be the AND operator. So that and 0 and 0 gives us 0. What do we have here? 1 and 1. Oh, that's going to give us 1. And 0 and 1, that's going to give us 0. And over here we have both inputs, so 1 and 1 is going to give us 1. So let's see here. Oh, look. This and this are the same. And this one here, we don't care. Doesn't matter. With this one changes, that is not affected. So look, this equation is true. That's another way you can look at when you want to solve things or simplify things. Sip of coffee. I'm talking too much. All right, let's keep going with this show here. Multisim, okay. Other laws, we have something that's called identity law. If we see this, whatever with 0, it's going to be that whatever here. In this case, we just use the letter A. And if you have whatever with 1, it is also going to be. But this one here is the OR operator. And this one here is the AND operator. See, these are different here. So that is a law. You see, from the philosophical point of view, what is logic? A logic is an environment within that environment, there are certain rules. And though the actions are going to cause true reactions according to that closed set that we are within, closed room with those rules written. So here's logic. So if somebody says something is logical or not, you can say according to what logic, according to what set of rules. And as I keep saying, your logic might be different than somebody else's logic. And as I keep saying, you will understand that when you get married. Okay. I'll never say that. All right. All right. Here's the annulment law. A or 1 is always going to give you 1. Well, of course. A or 1 will give you 1. Where's my board? Whoa. Here's the logic gate of OR. Two inputs. One of them is pulled high, the VCC. And this is going to be pull-up resistor. So this one is always 1. That one here, we could have another pull-up resistor going to the same VCC. We can join that line. But over here, we have a switch that is going to the ground. So there's normally open switch. We activate that switch. This becomes 0. We open that switch. It's being pulled up high. Right. So this could be either 0 or 1 at this point. And what is the truth table for the OR gate? Because that's the symbol of the OR gate right here. 0, 0, 0, 1, 1, 0, 1, 1. Right. OR logic. This one's giving us 0, this one giving us 1, this one giving us 1, and this one giving us 1. That's the OR truth table. So let's say this is input number 2, this is input number 1, and that is input number 1 is A, and this is B. So here is A or B, whatever, here. But since, if we have that, if we just copy one of those, all right, and the other one is going to make 1, 1, 1, 1, 1, because one of them is stuck high, and the other one is going to be 0 or 1. That's it. That's all the combinations we have if one of them is stuck high. Let's say this is A. No. This is B. B is stuck on high. And A, we're operating. What are we going to have? 1. This is going to give us 1. This combination is going to give us 1. So A or 1 always give us 1. And you can do the same action. You can apply the same course of action to the AND gate. But if you have A or 0, that's always going to give you 0, because with the truth table of AND gate, we have to have both of them at 1 in order for the output to be 1. Idempotent laws. A and A, that is A. Draw it like that, well, just like I did. You're going to do the same thing. You're going to prove it. A and A is going to give you A. That's the law. Inverse complement law. A or not A, that's always going to give you 1, because it's OR operator. And A and not A is always going to give you 0. You just have to train your eye to see and fish those out from the big complex equations. Commutative law. That's probably the easiest one here. A or B, same as B or A. Right? A and B, same as B and A. Right? Not spending time on that. Associative law. A or B and C is same as B or C. So with the OR, that's kind of like expanded. It's almost the same thing here, right? You can just drop the brackets here altogether. And over here as well. Yeah. But it just had to be written. Double negation, it had to be written. Not A equals A. Negative of a negative is positive. De Morgan's laws, we have done considerable amount of those. Now here's an interesting one, because why is it that we study all this? Among other things that you're going to need this for, but the gist of our class is to apply this knowledge to the PLC logic. And the programming language that we're using is the ladder logic. Well, if we have some kind of like an AND gate, it's easy for us to implement that, because we have the rail and we have the rail, and if we want to do AND operation, we just go examine if closed and examine if closed, and that is going to give us the output energize. Right? Examine if closed, that should be I, not L, and then output energize. So that's an AND logic. How do we do OR? Well, OR, we're going to have a couple of rails, and we're going to have examine if closed, output energize, and we do a branch. This also examine if closed. So this could be input A assigned to the physical input, and input B input B is also examine if closed. That's the symbol of that. So whenever you activate this switch or activate that switch, here's the OR function, you're going to have the output energized. And remember, the XIC, which is examine if closed, here's the symbol of that. It's looking for the logic 1, the logic level of 1, to pass the logic through. So if this one gets logic 1, it passes the logic, not passing the electric current, because this is software. If we use the ladder logic with the hardwire system, then we will be talking about passing the electricity, passing the electric current through. But since we are talking the software here, then we're passing the logic through. Or we can call it logic continuity is being passed on. So this one is looking for logic 1, for the logic continuity to happen through this instruction. And this instruction is in the form of normally open contact. Here's the switch. Now, the examine if open, is looking for the logic 0 to pass, for the logic continuity to happen. And That's here, and this is going to be represented by a switch, like that. Push that switch, and it gets logic 0, which means the physical input gets 0 volts. Applying 0 volts, or not applying 24 volts, because the PLCs work on 24 volts. We drilled that a couple times during the lectures in class. If we have 0 volts applied to the physical input, that instruction is going to pass the logic through and is going to give the bit of 1 on the output energized. And if the output energized sees the bit 1, it is going to apply 24 volts to the physical output. That's if we alias that output, if we alias or if we assigned that to a physical output. We could assign that to something else. We could assign that to a bit that sits in the memory, and we can call that something wherever it sits in the memory. We call that something, and we can assign one of these to alias that. So if it's looking at the bit 0 or 1, it's going to react a certain way. So this also can be assigned to the physical switch, or it could be assigned to look at the bit that's stored in the memory of something. We've gone through that as well. Well, so it's easy for us to do this stuff here with the AND gate, with the OR gate, with the NAND gate, with the NOR gate. We went over that. With the inverter or the buffer. And buffer, by the way, is the yes gate. And the inverter is the not gate. But how do we apply this weird kind of a exclusive OR? We have to transform that into something that can be used in the ladder logic, and that's how we do this. Where did that come from? This equation here. How do we get that? All right, what is the truth table of the exclusive OR? Here's input A or input B. 0, 0. Here's A. Here's B. 0, 1, 1, 0, 1, 1. Just the combinations here, and that's the exclusive OR. Here. Let's make it nice and pretty. So exclusive OR is going to give you logic 1 here and logic 1 here. As long we need one of the inputs to be on, to have logic 1, for that to be on, to output to be high. Anything else is going to give us logic low or 0 on the output when we have that exclusive OR. If it were just OR, then this would be 1. Well, by looking at the truth table, look at this here. In this case here, we have two conditions here. This one here gives us 1, makes it true, and it's true in this condition right here. It's going to give us also true logic, or logic of true on the output. Anything else is not going to give us true. So the output will be true when we have, in this case, looking at this truth table here, this condition or this condition, so we're going to have OR in the middle. And over here we have two inputs here and two inputs here, and we have A and B, and we have A and B here, because that's the only thing that we have they're dealing with. And it is the, in this case here, we have this and this happening. So we have the operator of AND here, and we have the operator of AND here. And in this first condition, we have not B because it's 0, so not B. And A is 1, so we leave it as is. On the second condition right here, we have B, so we leave it as is. And we have not A. So this here is the same as this right here. It's just in different order. So here's another way of looking at this, how you can actually come up with this. Now, stay there. This is applicable on the ladder logic. We could, it's doable. How will we do that? We're looking at this here. All right, we have a rail. We have a rail. We have an OR, so we're going to have a branch. So in the rung, we have one instruction. This is going to be A, input A, and input B. But because we have that not thing, so this is examine if closed here, examine if open here, we apply this instruction. And that we're going to bring it to the output energize. OTE instruction. And then we have to do that OR. So we branch it. Stay like that. And we're going to have a contact here, or instruction, and the branch is going to close like this, like so. And in this case here, if this is A, again, and this is B, so over here we have to apply, on the first one we have to apply examine if open. Yeah. And the B here, we'll leave it as is, examine if closed. So of course, this one is looking for logic 1 to pass, for the logic continuity to happen. This one is looking for 0 for the logic continuity to happen. This one is looking for 0 for the continuity to happen. This one is looking for 1 to pass the signal through. And then if we apply that against the truth table, this condition will never happen. Actually, it might. Sorry. It might. If we have both, if this is applied to both switches, one, and over here we could have both normally open switches. We got 0 and 0 condition, or the input, physical input. Physical inputs associated with A and associated with B. These are the physical things that you plug things in. 24 volts is high, 0 volts is low. If you have both zeros, So 0 is going to give us, it's not going to pass the logic through. So this branch is broken. This one is going to pass it through, but it's going to stop before it gets there. So this branch is going to give us false. Again, 0 and 0 here we're looking at the first condition. 0 is going to pass it through, but 0 here is going to stop it. So we get 0 on the output. It checks out. Let's see here we have 0 and 1. So B is 0, A is 1. B is 0, it's going to pass through. A is 1, it's going to pass through. So the logic is going to continue through this branch. But this branch is going to stop it. But who cares? Because this one is passing it through. We got the other condition 1 and 0. Then this branch is going to pass the logic through, and this one is going to stop it. So the logic is going to travel through here. So we have that OR here. It's either this condition passes it through or that condition passes it through. That is the exclusive OR. Exclusive OR logic. All right, now, when you want to do the exclusive NOR, I'm not going to go through that. But the exclusive NOR, and this would be the symbol for the exclusive OR as well. Or exclusive NOR. Right? Or you could have it like this. It's not staying. Or you can have this symbol. And it's going to be like this here. See the differences between these two guys here? Exclusive NOR or exclusive NOR. That can also be applied through the ladder logic. We have A and B, or not A and not B, so we would just do this. And that is XNOR logic. We have to transform those into this. Now we're stretching it a little bit. That's why we took a little bit longer for the last class. That's why we had to wait. I have something for dessert here. Now this is, as I said in the previous class, I pulled up heavier gun here. It's this exercise. You can follow me as I go along here, but I'm going to encourage you, when I post that, you can download it, look at it, and look at it again, and look at it again, analyze it, make sure you understand everything that's happening, because this thing is, it has layers of psychological comfort applied here, if I can say that. It's one of those things that you have to be really awake and alert to be able to grasp this solution. And you have to do it in one shot, because if you look away, you're going to lose it. You have to do it from start again. All right, so here we have an expression. This is the expression that we have. Simplify it. Using the distributive law, and of course you can't escape. You're going to have to apply other things as well. Step number 1. Let's see what can we do with the distributive law. We can't do it one shot. We can separate this one here and leave this one alone for now, so we can see if you can reduce that one and then add that one there and see what else we can do with this. So for the distributive law, where do we have that? We have A or, well, not A and B, or A and B. So we have three terms here. We have something that is ORed with some other two terms that are ended, or AND, with the AND operator. Do we have that somewhere with the distributive law? Right here. Yeah. You're going to have to see that. Train yourself on seeing things like that. So, if we have that, A or B and C, that is going to give us the A or B in brackets here, and A or C in also brackets. So, did I say don't look away? We just looked away. But let's get back onto the wagon here. That here. So use the distributive law, which states, and we're just using different letters here. X or Y and Z equals same as X or Y and X or Z. So we're just going to use that analogy and apply that, X, we're going to make A, and, Y not A. So we just skip no steps, write those down. That's why I'm stressing it out always. Skip no steps. Engineers have tendencies to do that. I am not a fan of that kind of thing, right? But hey, after a while, things are obvious to you, so that's, you can do that. But now, don't do that. Just write everything down, every little step. So, yes, we assigned those letters to that. Okay, so now, by that analogy, that A or not A and B, we can write it out like this. So we have this, just substituted that. Just that. But then, of course, we have to carry on with the other stuff. So we have to add that or not A, not B, and not C, because that still exists. But we just took care of this part here. Is there something else we can do with that? Oh, look. A or not A. Is there something that we saw that? A or not A. Do we see that somewhere? Oh, here it is. A or not A, that's going to give us 1. Whoa. Why don't we just do that? So this here, we can just substitute with 1. And here's this, write the step. Copy that expression here, and this becomes 1. So you could write it. Now, we have other laws. 1 and something else becomes that something else. There you go. 1 with something else becomes that something else. In this case, that something else is the expression in brackets, where are we here? There you go. 1 and this becomes just this, so we can drop that 1. So now, that expression becomes A or B. There you go. This here now is this. A or B. So now we got A or B or not A, B. Now we could, here's the end. We could De Morgan that. What's that going to give us? A and B. A, B. It's going to be the same. If we De Morgan that, we can join the line, but we have to change the operator A or B. That's the De Morgan theorem. So then there's that whole complex thing that when we see this is what the and see, that's where we're at right now. That's where we stopped. To simplify further, A or B as a single term and distribute it over final term, this A, because we still have to keep that. That's the other part of the equation. Now you see, we demorganize that, so that gives us A or B, complement A or B, so demorganize that. Negate that, follow that. This one here, you have to do it few times. You have to, this is probably the most complex thing to grasp. And unfortunately, there is no any other way, but you just have to go through this, do it 17 times until you get what is happening here. That's the most intense operation that's happening here. But when we demorganize that, and you see here that we just let the W, which another, we substituting, simplifying things so we don't have to write things. So we just say, okay, let's A or B to be W. So not W equals A or B if we negate that. So then here's the expression that's happening, that the W equals not W and C. And then if we substitute the W for the A or B, from one thing to the other, to the other, to the other, we're going to have that A or B or C. And I wish I was able to relay this thing more clearly. But you were just going to have to stare at this thing, look at this thing, and grasp it. I can only go so far with talking about this. If you don't, see me and we will write it out in more detail. Or we can take it up in another class. But after we demorganize that, simplify it, reduce it, here's the final answer, A or B or C. So this here equals to A or B or C. That's how we approach this thing. And I pulled out a heavier example because I want you to kind of Like this is not just the distributive law that it applies. It applies pretty much everything else. But once you grasp that in that one exercise, the other stuff is going to be simple for you. All right, we've gone over it. No, well, you got the proper time right now because we started 5 minutes late because I was waiting for the software to complete its thing from the last class before I could start this class. So that's it for today, folks. And I will see you tomorrow during the lab. All right, have a good breakfast and see me tomorrow. Thank you.